Technological check. Can you hear us?
Hello.
Good afternoon.
So do you hear me?
Yes, we can hear and see you.
Thanks. Okay. There are some technological issues today. I don't know why. My presentation is not so it's not working as it's supposed to be. Well, okay. As usually, I'm waiting for another like a minute and trying to deal with the presentation in the meantime. So please wait up. It used to work okay yesterday. I was testing, and today the tool that is that is converting LaTeX mathematics into HTML is not working properly. So there is no mathematics in the presentation. I don't know why. And I don't have a PDF version. Okay, we'll try to deal with it. So we are continuing to deal with stationarity of time series, and hopefully we are going to finish the stationarity testing today at least. This is the minimum that we have to do, but we have a lot of stuff to deal with otherwise. And with this troublesome presentation, I'm not sure if it's okay. I will try to write everything that is not visible there, and when it works, I will upload the presentation that is okay. I hope that it works, or maybe some update is required for that library that is used to output mathematical symbols and stuff. But yeah, let's see. So just a quick stretching to begin with. Very simple questions, but please pay attention anyway, because you've already had your practice session, and this is the point at which we stopped the last time, exactly the same. So before we come back to the concept of stationarity and so on, this is something that should be really easy already for you. We have a few time series examples, like real life time series, like this one, the Big Mac index for American dollar to Russian ruble exchange rate. So first of all, before we get to the stationarity question, the one that is the most important for us, do you understand what this series represents? Is it familiar to you? Who can explain what it means?
The Big Mac index is the quality of life in particular country. And because we can find everywhere, I believe, McDonald's, so it's quite a good index to measure.
Not exactly
to measure
quality.
The price. That means not just quality, but the price level in the country.
But this is about two countries now. You see, it's about two currencies.
It's an exchange rate measured on the burger. So it's just exchange rate without politics and other stuff. So we can, for example, in 2019 buy $1 for 20 rubles.
Yeah, so exactly. This is not a market exchange rate. You cannot actually buy dollars and rubles or sell vice versa at this price, at this exchange rate. But this is something that is a proxy of the actual exchange rate, of the actual value. What does PPP means? What does PPP mean?
Паритет покупательской способности?
Yes, that's it. Purchasing parity, purchasing power parity. Yes. So yeah, that is related to the Big Mac index. That essentially Big Mac index, as Vera correctly said, it's not a quality of life, but something related. Like it's like a very restricted measurement of inflation, or measure of inflation. Why very restricted? Because it's based on one single good, not on a consumer basket, for example, like sometimes it's done, but on a single good. And there are many single good based indices in the world, and this is one of the famous because it is easy to explain to the general public outside the field and outside the professional fitters, and sometimes it's used. So yeah, it is often it is criticized for its like bias in it in some sense, but still, so there is something behind it, some intuition, and it can be explained. And then based on the inflation, we can also construct the real exchange rate based on that thing. So yeah, so approximately this represents the dynamics of the real exchange rate of the American dollar to the Russian ruble. And yeah, as you can see, it is a lot different from the official like market-based or central bank controlled exchange rate, because it also accounts for inflation and it's based on a single good. Now to the essential question. What about stationarity? And I am reminding you, stationarity, when we are talking about the data and analyzing the real lifetime processes, or potentially what we can see in the data and distinguish between stationary and non-stationary, we mean only the so-called weak stationarity or second order stationarity. So I'm not talking about the whole distribution of that thing at each point of time or joint distributions. This is about stability, somewhat like stability in time of what? Of two characteristics at least, or three. It depends on how to count. What kind of stability are we looking for when we are looking for stationarity in the data?
Mean variation and outer correlation.
Yes, so the first two moments, and then this is the general for the two characteristics, the first moment and the second moment. And the first moment is just a scalar value. It might not be a constant. This is the question of stationarity or not. But it is a scalar value. And the second moment, it's like a whole collection of numbers, because there's variance, not variation, because variation is a general like characteristics. Something can be variant or not variant. There might be some variation or not variation. When we're talking about numbers, numerical characteristics, the dispersia is variance. So variance and then also outer covariances. Both variance and outer covariances are what are the second moments. And by the way, notice that we haven't talked about looking at outer covariances at all and the dynamic of outer covariances in time. There's a reason for that. First of all, usually we don't care about that much when we are talking about the data. And if the time series is not stable on average, or like in the mean level, it's already non-stationary, so it's enough. If it shows some signs of heteroscedasticity in the variance, it's already also enough for it not to be stationary, and then it's not necessary to look at the outer covariances. And vice versa, which is not as simple and as logical, but still in practice, we tend to look only, or to consider only, the average level and changes in the average, and sometimes, but sometimes even ignore that, the variance. So the change in the general level of variation, dispersion, and well, by that to measure variance, yes. But autocovariances, we normally assume, so yeah, if the variance and mean are stable, then probably autocovariances are also stable. It is a lot more difficult to observe autocovariances from the data and not as easy to to see the change in it, but it is possible. So what about this particular time series, the Big Mac index that shows exchange rate? What should be our conclusion should be about stationarity? Stationary, not stationary, maybe, and why?
So even before looking at the graph, we can say that it is highly unlikely that it will be stationary, because that index is influenced by many shifts, and of course by heteroscedasticity.
Heteroscedasticity is a little bit too much to see from that graph, actually.
No, just before seeing that graph. So, like by economic judgment.
Yeah, okay, so that's a crucial point, thanks. Economic judgment should come first, right? So even before looking at the graph, this should be already okay. So this is something strange. It might be based on a very restricted basket of goods or based on a single good, but it is still an exchange rate. And exchange rate is a kind of price. That's one of the important macroeconomic indicators in macroeconomic analysis, macroeconomic in understanding of the macroeconomy of the world, of the countries involved in this particular currencies exchange. So it is very unlikely, as you said, that it is stationary, even without looking at the graph. There might be some periods in time when we can observe such data for this time series process, that we won't be able to distinguish this process from non-stationary, just for a particular portion of data. This is not a reason to conclude that it is stationary, because yes, as you said, we know from the history, we know from the macroeconomic theory, we know from the general whatever reasoning based on like just general observations from the reality, not necessarily from the theory, that there are many shifts. It is normally subject to a lot of events that take place in real life, and hence, yeah, it will not be stationary. The most likely types of non-stationarity that we would observe are what? You mentioned heteroscedasticity. This is not the most obvious one, but what would be the most obvious types of non-stationarity that we should expect from this time series?
Structural shifts?
Yes, because of influence of many events, yes, and something else? Or just structural shifts? Okay, now we can look at the data, at least at this portion.
On the data, we can observe some kind of slow growing trend, but I'm not sure.
Yeah, it's trending. It's definitely trending. Just look at the first and the last portion of the data. The average level definitely changes, and you see that the change is quite gradual. It's even if it's a structural shift, because it only covers 19 years. Well, normally, if something gradually changes over 19 years, it's already not fast enough to consider it even as a slow structural shift, because sometimes structural shifts happen also slowly, not immediately. But if it's gradually changing over 20 years, it's already a trend for sure. So it's trending and it's growing overall. Not always. but it is quite persistent, that tendency to grow. Oh, okay. Further discussion of that time series is going to take us to macroeconomics. This is not our objective. So it's not stationary. We should not treat that thing as stationary. A more complicated example. Again, the same question to begin with. Do you understand what this series represents? What is it? So first of all, of course, it's a dynamic series, time series, something. From the name, we understand that at least it's annual. So the previous one, by the way, it was missing from the title and from the description, but it was obvious from the graph itself. It was monthly, and not monthly, but quarterly, I think, something like that. Now it's annual.
So Gini index is roughly speaking is the index of inequality in the particular country.
Yeah, why roughly? It's not roughly, it's the principal metrics of inequality. When we are talking about like macroeconomic level measurements of inequality, this is like the leading one. Yeah, so this is an inequality measure. What can we say about the range, the possible range of the values? Do you remember the scale in which it lives?
From 0 to 1?
Yeah, from 0 to 1 or from 0 to 100, like in this case. You see on the vertical axis, the values like vary from 37 here at the bottom and something like 43, 42 and a half at the top, at the maximum. Right, so this is like a percentage scale from 0 to 100. Okay, what about stationarity? Essentially, then visually.
Essentially and visually, definitely not stationary.
Okay, not obvious to me, at least until you explain.
Because essentially we know that from 90s to our time, Russian economy was changing substantially, because for it was planned economy, and it's clear that incomes was very equal. But then market economy was developed and the inequality was raised.
Yeah, first of all, this sampling here, it starts in late 90s. It was already like almost a decade after the crash of the planned economy. Also, the equality of the income in pre-market times is an exaggeration. It is difficult to measure, because if you base your calculations on the official statistics from that times, the incomes are not what they represent nowadays or in the national account system, for example. So it's very difficult to measure. Also, there are certain problems of the statistics as well. So the time series even would not be able to construct, at least it's not as easy to measure inequality based on the same index and compare planned economy and market economy. At least not as close. So you cannot like compare them so close to the transition. Maybe like decades after or century after, then we can say that yes, then those times and these times. Well, yeah, so this is not the question here. So imagine that we are talking only about the market economy times. But still, so yeah, you're right. There were 90s that were a lot different, like the right after the establishment of the market economy, and then there was the crisis close to the like late in the 90s. Then there was somewhat growth. Then again, the crisis, and so on. And of course, it influences the incomes of the population and the distribution of the income and inequality. So yeah, so at least it's subject to structural shifts and changes.
And moreover, it has several trends.
Yeah, and those shifts, they can be observed like changes in trends. So it grows during some times, it decreases during some other times. Sometimes it remains somewhat stable on a certain level, but that level around which it remains stable also can change over time. So there are shifts of different kinds. We can observe shifts that change the trends, or shifts that change only the stable average level. Those are different kinds of shifts, yeah, like change of the direction of growth to decline, or from growth to stronger growth, or growth to milder growth, and so on. Those are also shifts, just a different kind of shifts. Yeah, so substantially, it is not. It should not be expected to be stationary. Given a small sample of data, because it's annual change, and even though we know that during this time there were a lot of substantial changes in the economy, unless we dig deeper into what happened to inequality in particular, we should not make a conclusion probably. We can expect non-stationarity, but who knows what happened really. And from the visual analysis, we see that, yeah, a lot of changes appeared. This kind of data might be tricky because it's limited. It cannot go beyond 100, it cannot go below 0. Still, it doesn't mean that it will be stationary inside this data, because of all we described. It still can be trending, it still can be like stable over some time around some level, then change that level. And that cannot be considered as stationary. Another thing of those macroeconomic things, they are often subject to cycles, right? There are business cycles, there are periods of economic growth, expansion, reduction, declines, and so on. This is again taking us to macroeconomics, but which is not necessary. But it would be like observed like some kind of oscillation. It is very easy to mistake business cycling with trends or like with substantial trends that don't change, or even sometimes with stationarity because of small samples. That is why the essential judgment should always be like the first thing to do before the visual analysis, because if we remove all the information about what this data represents, essentially it is not as obvious if it is stationary or not stationary. It might be very well a sample of a stationary process if we don't know the nature of it. In this case, we know the nature, we know it changes substantially due to some essential changes in the time in the data generating process, in all the factors that influence this whole context of inequality. So yeah, of course, not stationary. Something else, maybe even more complicated. Again, the same question, the same kinds of questions. First, what does it represent? Is it clear what it means? And then stationary or not? And someone else, please. Someone who did not talk yet. You can talk in Russian, it's okay.
It is a percentage here. Maybe not percentage, but the доля. Yeah.
For the graphics, and this is done intentionally. You see, sometimes there are, yeah, my internet connection is unstable. Can you hear me?
Yes.
Now, yes.
Yeah.
Yeah, okay. So you see, there I intentionally make some like skip some essential stuff from the graphs. You should not do it when you like write a project or term paper and so on. But now, because we are discussing and I'm asking you questions, this is okay. This is for you to like notice stuff. So this is a very good and on-point question. What kind of change is that? I doubt that this is percentages, you see, because of the scale. It is like between plus 0.05 and minus 0.1. So it's not percentages, because you know the history of the recent demographics of our country. it is not percentages, it's like growth rate, I suppose. Not growth rate, but change rate, right? If you multiply it by 100, then it would be percentages, yeah. And annual change, it means that it is the change between two consequent years and divided by the value of the previous year, of the earlier of those two, right? This is the annual change. That's the annual change if T is multiply it 100%, and then you are going to get percentage annual change, which is almost the same. And normally when we analyze the data, when we don't bother about nice plots and so on, we only take this because it's easier to work with when you model stuff without thinking about percentages. It is easier to interpret coefficients of the models then and so on, just to work with numbers that are between -1 and 1, for example, something like that. So
before we see the graph, essentially we could say that it's a good maybe of measurement to try to find stationarity in this data, because of like that this data is annual change, and that is good for time series, as we know from our seminars. And now, as we can see on the graph, that's we also can predict that there is might be a stationarity here, but maybe we need some calculations to be sure for that.
Yes. So you see, in our examples, we have less and less sure examples. That's intentional, of course, because we started that it is easier to reject stationarity than to accept it. When we have obvious reasons to reject stationarity, we reject it right away, like here. It's trending. It's exchange rate, not transformed. Values of exchange rate, of course, it's going to be non-stationary, and it's trending during the period that we observe. So yeah, non-stationary. This thing, boom, yeah, subject to economic cycles, subject to structural shifts in the economic context, crises, changes of economic regimes, and so on. And this thing, yeah, first of all, it's already transformed, as you said, yes, and often like one period change or several periods change even is a kind of transformation that is going to take our data from non-stationary to stationary form, or at least it will remove some kinds of non-stationarity. What do you think is the average level here over this time period? This time period covers from 60s to like almost 20, well, 1918 or 2018. What's the average level of annual change here, approximately?
-4%.
Yeah, something like that. Between zero, definitely. Well, not definitely. We would have to calculate that, but I suppose it is safe to assume that it is negative. And yeah, closer to -5, but probably somewhere around 4, 3, 5, something like that. Not unlikely 5, but yeah. So on average, it was decreasing the original data, the original number of H10 males in population. So H10 males in the population, that's basically the number of 10-year-old boys in the population, right? It was decreasing over time. Not all the time, but mostly more often. How can we see that it more often it was decreasing? from this data alone without any assumptions. This is something that we can say for sure, that more often it was decreasing than increasing.
We can
Just
we can compare periods when the graph was going down and the periods when the graph was growing.
That's not gonna answer the question that I asked. The original number of the H10 males, this is the annual change that you observe, right?
I think that we need to compare just periods when the value is positive and the periods when the value is negative.
Yeah, so this is the percentage change, and the original value, this one or this one, it's positive for sure. This is a population or some part of population. So number of people, it cannot be negative, right? Yeah, this we don't need. Then whether the original time series YT was growing or declining is shown by the sign of it, of this change. When the change is negative or was negative, it means the original series declined, right? That's just that is. So it was less than 1 year before it. When it was positive, it was growing. Done. So the signs of the annual change show the direction of the original series right away. And
we lost your signal.
then the periods when it was positive. Actually, it is not that obvious now when I started counting, but yeah, we can. Oh, damn it! The connection again.
Now you're back.
Yes, I am back now. I see. Unfortunately, Zoom only shows me when the connection that connection is unstable. Only when I come back from the unstable connection, and it does not indicate it when it starts. Yeah, I must say Monday's afternoon is not the best time for online classes, unfortunately. I am considering changing it some way, but it seems that it is impossible at this point already. So I will try to look for like maybe alternative connection or something. I used to use mobile connection before it worked better. Okay, so next time. So now when I started counting the actual points, it's not that obvious to me. If we had more positive values of the annual change than negative ones, then we would say that, yeah, it was declining more than it was growing. The actual value of those declines was also quite strong. It was declining sometimes over several periods quite strongly, right? More than 5% in 1 year decline. What do you think this could represent? What does it mean? Like 6% decline in the number of H10 males in population over 1 year. It is a strange measure, but it makes you think about the original data in a specific way.
Точка перегиба.
No. How could it happen?
So the boys who were 10 like the previous year, they got 11, and there were not as many boys who are who were 10 at the moment. So the population was getting older, something like that.
Something like that, yes. It is the sign that the population is getting older. Not this particular series, but if you take a similar series for different age groups, like age 10, age 20, age 50, and you see the same thing, like it is becoming like declining. It shows, first of all, it will show that the overall population decline which is probably too high mortality when you see it across all age groups. But also it will show you signs of aging population, because it doesn't mean that like there was high mortality. Probably there wasn't high mortality in this age group, right? It's like young male population, really young, not infant, not adult, not elderly especially, so young boys. So it basically means that most likely there were a lot less new people born, at least new boys born 10 years before. So yeah, in some sense, it shows some tendency of aging population in the future. Well, yeah. And then again, the same early in 2000s. And we see the results of it pretty much now in the adult population already around this time. But now it's growing. So this is the sign of growing population, first of all, and then
We lost you again.
okay, what about stationarity after all? Can we say that it is stationary? So as Vera said, that we might not be sure, because essentially this is already a transformed data and it's already changes. So they might have some deviations from the average level. Sometimes it is lower, sometimes it is higher. And it definitely indicates that the original series before the transformation, so just the number of Russian age 10 males without changes, that was non-stationary. It was more declining than growing, probably. So non-stationary. But this transformed series. So the conclusion here that probably it is not enough, because essentially it might be stationary. We don't know. Maybe we are not like specialists in demographics. That is also possible. If we were, we could have come up with some ideas why it should not be considered stationary. From the graph, we don't see any major changes, right? There are some like deviations, but then the series comes back, and it might be a result of non-stationarity. It might be just a random deviation, or not random, but due to some information, but then it goes back. So there's not a single conclusion based on the data. And again, as we said before, this is just a good example of this concept. It is easier to reject stationarity than to accept it. So there are not many reasons to reject stationarity in this case. It is not also a reason to accept it. This is help me please. This is a kind of famous fallacy of that kind. Appearance to ignorance, right? Something like that it's called. So just because something cannot be proved false, it doesn't mean that it is true automatically, and vice versa. So yeah, there is not enough reason to reject stationarity. It doesn't mean that we should accept stationarity. So some additional analysis might be required. This is one of the topics for today's class and for this week's seminars as well. Please pay attention to the following general discussions, because they are going to be very basic, and in the practice sessions you are going to build on that and expand the analysis. So some of the new material will also come in the practice sessions. We decided that more technically complicated stuff, it is easier to discuss with examples, like with more writing on the board and so on. So, and also seminars have more time than lectures. So this is only the basic ideas in discussions, and then you are going to expand on that during the practice sessions. So quick recall of what we saw last time and just now in the example. So why it is important to discuss stationarity in general. I am not asking you now, I'm just reminding you. So we decided, or I announced, that we are going to study time series as a set of tools that is applicable to time series analysis, because time series data is a lot different from the traditional random samples or independent and identically distributed IID data. the most essential difference or change from random samples is that the time series data are ordered and they might be dependent on each other. Sorry, just a second. They might be dependent on each other, and it means that all the tools that we studied for random samples that are designed and adjusted for IIDness, randomness of the data, independence of the data, like law of large numbers in the original formulation that you know, the traditional and the basic central limit theorem, the properties of like other convergence theorems and so on, the properties of the traditional classical estimators, like ordinary least squares, that is метод наименьших квадратов, ordinary least squares, MNK, OLS. Instrumental variables, whatever, maximum likelihood based on IID, those all are not guaranteed to work as well as they would in the case of time series, as they would in the case of random samples. So we need to study the another set of tools. And luckily for us, many of the tools with some adjustments, they have the so-called versions for stationary and ergodic time series. Ergodicity we moved aside, and now we're working with stationarity, because stationarity is something that we can observe from the data, at least the one that is so-called weak stationarity. But luckily for us, those theorems, those results, those properties that we need to use the econometric tools with time series data, they can be used with weak stationary time series, because strict stationarity is a very interesting but too strict concept. It cannot be observed from the data. When we are talking about observing stationarity from the data, we can only say about weak stationarity. That is like somewhat like stability of the first two moments. So yeah, we can observe from the data. And we said that rejecting stationarity is a lot easier in real life than and observing real data than accepting it, because we have essential judgment, we have visual analysis, and we can we know the most common types of non-stationarity that are what? Trends, structural shifts, heteroskedasticity of different kinds, shifts also of different kinds, and so on, that can happen due to some random shocks or because of the influence of some factors, especially in such complicated dynamic systems as economies, especially if it's macroeconomy or world economy, especially, and so on, or something else like a market, and so on. And we discussed several examples already, and you also discussed in the practice session. But as we saw, and you saw in the practice sessions, or we just saw in our examples, so formal testing is something that is also required. Sometimes when we cannot reject stationarity right away from economic judgment, from visual analysis, from our prior knowledge, intuition, theory, and so on, we might want to run actual tests on the data. It makes no sense to run the tests on the data that we know that it is not stationary. But when we are not sure, then yeah, okay, so it's time for testing. Now it's comes the hard part, not because it's difficult, but because the yeah, so it's formal testing of stationarity, but because the presentation is not, yeah, it's not it's not outputting the math correctly, unfortunately today. I don't know why the Majax library is not available for some reason, because it's an online library that is uploaded dynamically to the presentations, whether it's local or uploaded somewhere, and it's not working. So I will try to like go over everything once again and again and write down stuff. This is a very basic example that is very, very well familiar to you. Don't like let this crap that happened to the mathematical equations here distract you from the essence, please. This is just a very basic example that you saw many times in econometrics course. One sample, two-sided z-test. well, in econometrics course, we called it traditionally t-test, following the textbook that we used, but in other literature, it is used z-test. So who remembers? What does it mean? What means one sample? What means two-sided? What means z?
So we used the test only on one, how to say it, sample. So one
one sample of scalar variables. Yeah, that's
yes.
here. Yes, x-axis, some value, not a vector but a scalar. Yeah. What else?
So it was two-sided. So the alternative hypothesis was about being greater or being below.
So sorry, what the alternative would be?
Alternative could be greater or below
So
zero.
not equal, yeah, not equal, just not equal.
Yes.
The null hypothesis is about equality as usually. The alternative, this is the called two-sided. It could be there or there, so just not equal. It should be here. This is the slash neck is the not equal. Yeah, it would be easier to read if it was represented correctly, but no. Yes, so you're right. And z-test or means what? This is essential.
That it is made on a standard distribution.
Yes, it is asymptotic and it's based on standard normal distribution, unlike just classical t-test that is finite sample and based on t distribution. So yeah, that's it. I'm not going to stop in so many in like too much detail on each of these questions. It was essential before when this course was not following econometrics right away. Now I think you have all suffered enough pain from basic tests, so you remember what the hypotheses are and you just said. So yeah, the hypothesis here would be about equality of the expectation of just a single random variable to some. Yeah, I should write it, otherwise it's not impossible to read. Sure.
We don't see what you write.
Yeah, me neither. That's the internet connection problem. Yeah, now you should be able to see it. So we have a collection of random variables or a sample of the same random variable that is drawn randomly. So this is IID data. We have the null hypothesis that the expectation of this random variable is some constant mu versus the alternative hypothesis that is two-sided. So same but not equal. So it could be less, could be higher, doesn't matter. This is how the hypotheses are constructed. And then the questions ask, what is a statistical test? This is the crucial point here, where we're just bringing it to the context of conventional statistical testing. What is statistical test? Or more precisely, or more formally, a conventional statistical criterion. Just in your own words, what is a test? Not the full definition of the z-test, just in general.
So it's a statistical procedure which helps us to find the statistical basement for our hypothesis.
Yeah, something like that. So this is a very rough scheme of what a statistical test is. Statistical test is a procedure. Sometimes we call it a function, but it is not one-to-one function. So it's a mapping of some kind. Or we can call it a procedure that takes the data and everything that we know about it So all like the hypothesis and so on. So it takes the data and it helps us make the conclusion about the hypothesis, whether we should reject one or whether we couldn't reject one. And these days in the applied practice, people already like dropped that idea. You probably remember it from probability, of course, and even from econometrics, our econometrics course, that we never say that we do not that we accept a hypothesis. We either say that we reject or we couldn't reject. Отклоняется или мы не смогли отклонить. We never say that we accept. Никогда не принимаем гипотезу. So that's for practitioners, finally, decades, like hundreds years almost after. People now say, okay, well, that's bullshit. If we don't reject, we accept. So it's okay to say accept now these days, but still in the academic traditional courses, we say that, yeah, we either reject or don't reject. Just saying that because we never can be sure about any hypothesis, whether it's true or not in real life, because we never observe the population. We can only make a judgment and there's always probability of error, right? So those depends on the parameters of the test. But yeah, this is a procedure, and the conventional statistical criteria or traditional statistical tests, they work all in the same manner. We have test statistics. In this case, it would be T statistics or Z statistics. It's the same, just depends on the convention. Which is what? Who remembers? Well, there's going to be something like this in the denominator and in the numerator.
Разность каких-то...
Okay. Yes, разность. Yeah.
It's
of the estimated and the hypothetical value. Yeah. Hypothetical is this one, the one that is in hypothesis, right? The logic why the difference is in this way that yes, so the closer those things are, the closer the statistics should be to zero. And if we assume, for example, if our hypothesis was alternative hypothesis, if it was like this, that it is less of something. What does it mean in terms of the statistics? It means that when we estimate the expectation, and how do we estimate it? We estimate it with this mu hat, however it is calculated. It might be OLS estimated, might be just analogy principle, basic sample average, whatever, something, some kind of estimate that we believe does this, estimates the expectation. If we believe that this thing is actually true, and the expectation is less than the hypothetical value, then we would observe smaller value of that mu hat of the estimate, and this thing would be negative. The statistics would be negative. So this is something, because it doesn't matter what kind of difference you take. You can change the order here, right? So you can change those and then just change the test back. But the conventional form of the criterion is this. So if the alternative hypothesis is this, then this thing, the statistics should be negative to correspond to that hypothesis. So the more negative it is, the smaller this thing is, the more we should be apt to make the conclusion that alternative is more likely than the null. So yeah, this is it. And we say that if the null hypothesis is true, it means that this thing estimates something that is actually close to mu, or close enough, or exactly mu. Then as sample increases, this thing is distributed as normal 0, 1. This thing is called test statistics, which should behave in some known way under the true null hypothesis, right? And then we make the conclusion. We either calculate the test statistic, the Z statistics, and compare it with the critical value in absolute value in this case, because it's a two-sided hypothesis, right? or we calculate P value and compare it with our critical size value. That's the same. It depends on just the interpretation. So this, I think you remember, or at least I hope. I expect you to remember this, at least in some way. The closer the test statistic to 0, if it's small enough in absolute value or just inside the not rejection area, if the alternative is one-sided, then we don't reject the null. If it's too large in absolute value or too far from 0 inside the rejection area, then we reject the null in favor of the alternative hypothesis. That's it. All these tests work the same, right? So now, why is it important? Yeah, so that was it, the general scheme of the application. Why it is important to keep that in mind, because we are not going to use the conventional tests here. They look like conventional tests. They are conventional tests, just tests of different kind. It is not anymore a traditional t-test or a traditional z-test. It's something that is based on the same kind of statistics, but the distribution is different and the set of hypotheses are different. And this is important to remember. When we are testing for stationarity, formal tests of stationarity exist in different forms. There are like dozens of them, literally. We are going to consider two now, because this is the general, like covers the general idea of stationarity testing, exactly testing from the data, not based on the tests, not on essential judgments or visual analysis. But there are more tests, and some other tests you are going to see in the online course, and some other tests you are going to consider in the practice session. So the first test that we are going to use, and this is like practice proof, you will see it mostly often in the practice. Sometimes it is changed to something else. An alternative to this test you are going to consider in the practice session. But the ADF test, this is the name of it. This is how we usually going to call it. The ADF test is the most popular test of stationarity. ADF stands for Augmented Dicke Fuller. Расширенный тест Dicke и Fuller. Это фамилии, so names of the authors of the test. There are several papers that they published about the kinds of tests, and there are different versions of it. The basic ADF, like the basic version of ADF test, is the most popular one that is used in practice. It is not visible here, so I'm going to rewrite it again. So first, ADF. It is most important to remember what is the null hypothesis of the test and what is the alternative. So the null hypothesis of the test is the so-called unit root. It might not be clear what it is if you haven't started your online course yet. It is okay if it's not clear. It's just that you would see it in the online course. We are going to see what the unit root is later in our course as well, of course. Now, it is important to remember that the unit root, it's a kind of non-stationarity. So this test tests for a particular kind of non-stationarity. But normally, if there's one type of non-stationarity in the tests, in the time series, the unit root test will also capture it. Not always. For example, it might not capture heteroskedasticity if there's no other changes. But if there are not necessarily like unit root kind of trends, but other kind of trend, like explosive trend, for example, or if there's structural shift in the average level, then the test will also capture it and will distinguish non-stationary time series from stationary one. And the alternative hypothesis is stationarity. So that's it. The set of null and alternative hypotheses for this test is like this. So the null hypothesis is non-stationary and the alternative is stationary. Why is it important? Because other tests will have it differently. In other tests, you will see the alternative hypothesis is non-stationarity and null is stationarity. And it is important to know which test has which set of hypotheses, which hypothesis is which, because otherwise you will not be able to apply the test correctly. You will see low p-values, but will not be able to say what is the conclusion if you don't remember the hypothesis. Why the hypotheses are such and what unit root means, this is, so about the unit root we are going to talk later in the course, but why the hypothesis are such is like a topic far beyond a basic time series course. We need to go over like a particular non-stationary time series processes and probably not even discrete time, but a continuous time process and so on. So we deliberately leave it out. And this is how it's usually done, especially in practical courses. If you want to get familiar with why the test comes out as it is, then yeah, you should read maybe some very advanced time series books, but honestly, I do not recommend going to there because this is already a standard that is used in practice, and it is quite enough to know how it works and what usually the conclusion is, rather than to know all the theory that like lies underneath all the models and the hypothesis tests.
Excuse me.
Yeah.
So the mathematical determination of this test is also in those high advanced books, right?
Not all of it. Yeah, you can see also the mathematical formulation in some like simpler textbooks, but the whole explanation why it works as it works, yeah, it's in the papers, for example, by Dickey and Fuller, and also in some papers, but not even in all textbooks, not even in some advanced. If a textbook is going to be practice oriented, it will omit all that stuff because it's not crucial to understand the practice of using the test. So yeah.
Okay.
The form of the test, the actual test statistics, is easy. It is a kind of t-statistic. So it's calculated exactly as the t-statistic. There is some parameter, estimate, minus some hypothetical value over the standard error. Whatever that parameters that come from a model. The model that is under the null would represent a process with a unit root or a non-stationary kind of process, because this is and under the true null with asymptotics, as again, it will have something. It will not have standard normal distribution. Why not? Well, because it's time series, and remember that, right? So true null in this case stands for non-stationarity. It's not only time series which is dependent and so on, it's also non-stationary. So there is not a single distribution of this time series at each point of time. It changes. So the behavior of the standard of the statistics under the true null is something crazy. And this distribution, it exists. This is the subject of those papers, of those advanced papers, that the derivation of that distribution. It exists, it is calculated, it does not exist in analytical form. It can be tabulated. So it's not a distribution that you can derive a formula for it. But it can be tabulated, simulated. And statistical packages, usually they do what? They calculate the statistics, they have the table for this distribution, and they return you a p-value. Right, so, and then it can be it can be interpreted. It usually it is usually returned like this. Sometimes it's a particular number, but not very precise. Because the distribution is only tabulated, statistical packages will only give you like a range for the p-value. Too small p-values you will not see. You will see the result. The statistics is so high that the p-value is less than 0.01. It means that that the statistics is so high that the computer doesn't know it. There are no table values calculated for this value of the statistics. Why not? Because it's already too high. And for our conclusion, it is not necessary to know the precise p-value, because it is already easy to make the conclusion. What is the conclusion that we make when we see p-value that is definitely less than 0.01? In any other test?
We reject null hypothesis.
Yes, reject null. In our case of the Adf test, null is unit root, which is non-stationarity. We reject non-stationarity in favor of stationarity, which would mean that we make the conclusion that the data is stationary. Of course, at this point, it is very important that we already passed by all the stages of testing, right? We already analyzed the essential judgment, like try to reason why this time series might be from non-stationary or stationary process. Then we also analyzed the graphics with the plot, performed the visual analysis and saw that, okay, there are no obvious signs. And then we run the test and say, okay, reject it. So yeah, this is very likely stationary process. Same with this thing. Normally, this is the threshold that we use. When the p-values are less than 0.1 or 0.05, then yeah, we reject the null and conclude that, okay, this seems stationary. If not, then it depends. If it's high enough, then yeah, we could not reject. There's definitely a unit root, which is a non-stationarity. But it doesn't happen often, because if it is obvious unit root, you would be able to distinguish it from visual analysis and from essential judgment. Otherwise, it's really strange. If you rejected non-stationarity at the stage of essential judgment, if you reject the non-stationarity at the stage of visual analysis, it is very unlikely that you are going to end up with this range of statistics. It must be something wrong with either your judgment or with the test calculations. So it is a reason to reconsider. So those all judgment stages, all the testing stages should be coherent to each other. Otherwise, it's strange. This still might happen like around 0.1. Why not? So yeah, this is the description that I just saw. So under the true null, when the null hypothesis of non-stationarity is true, critical values can only be tabulated. This is a non-standard distribution that's called the DF distribution or ADF distribution. And this is an important property. Let's not stop at it too much. You are going to discuss it in the practice sessions. But try to think about it, like give it some thinking. Under rejects false null. What is false null? Null is non-stationarity. So if we feed a really stationary time series there, it is false null, so not unit root. It tends to reject false null. Under reject, so rejects not too often the false null. So it might confuse data that comes from stationary, non-stationary. That's why we don't use this test alone. In some sense, it should be like intuitive. It tests only for one particular kind of non-stationarity, that unit root, which we don't know yet what it means, but it is a one particular type of non-stationarity. It's a kind of trend. And based on a one single kind of model. Yeah, it's very powerful test, not too powerful in statistical terms, but yeah, it is a very powerful test used in practice very often and so on, but still it has problems. So sometimes the conclusion from this test alone is not enough because of those problems. And then we use a different kind of test. And there are many alternative tests, and it is important that you use essentially different kind of test. Because, for example, an alternative test to DK-Fuller test would be the so-called PP test, Phillips-Perron test. You are going to talk about it in the practice session. But essentially, this is an alternative. This is like not just an alternative. It's another version of DK-Fuller, just a minor, sorry, minor adjustment. Same set of hypotheses, a very similar model, a very similar judgment. And it is important that you use different kinds of tests. And an example of a different and essentially different test is, for example, this test, which we just shortly call KPSS, because it's very hard to pronounce the full name, Kwiatkowski-Phillips-Schmidt-Shinn. So KPSS. And again, it's not readable, but the essential difference is that it's based on a different kind of model and compare the hypothesis. Well, it's not easy to compare without math represented normally, but still the hypotheses are like the opposite. This is the second test. The null in this hypothesis is stationary. And the alternative is not stationary. There is also some test statistics. It's partially non-parametric, blah, blah. So there's even a weird mathematics behind that all. But the idea is the same. The statistical packages will throw out p-values. It usually gives you the following range. It says either it is less than 0.01, or it is higher than 0.1, or something between. So either this, or some value that is between those two. And again, so if this happens, we say, okay, reject null in favor of non-stationarity. If this happens, we say, okay, the p-value is too high, we cannot reject stationarity. So we make the conclusion in favor of stationarity. And something in between, then it depends on our particular alpha. If our alpha is at 5% level, then yeah, so same kind of thing. So you have to make this threshold yourself here. Usually it's at 0.05. Whatever is there, then the conclusion that it is not stationary. And here it is stationary. Done. The important thing is just not to mistaken the test, or not to confuse the test between each other. So to remember which has the which kind of null. So this test is very rarely used on its own because of its very specific model that is underlined, but it is used to like double check and confirm the results of different tests, of other tests. For example, of unit root tests such as Adf test, or the other one that I mentioned, the Phillips-Perron PP test. So back to the presentation now, mathematics is not going to be there. So this is an example from previous lecture which we did not consider, but you saw it in the practice session, I believe. The dynamics of yearly percentage change of USA import of goods. So what does it mean? What this series represents? Without looking at the values of the tests and so on, just about essentially about the series.
So it's one of the main macroeconomics variables.
Well, a transformed value of one of macroeconomic indicators. Yes, so not macroeconomic, maybe like international economics, macroeconomics related indicators for a big open economy such as the United States economy. Yeah, it's one of the indicators. Maybe it would be even more important if it showed the dynamics of ratio of imports or like share of imports in the gross domestic product. It is more often used. But now we are talking about the percentage change. So it shows somehow changes in the trade dynamics, right? So the country imports and exports a lot of goods of different kinds, and this is somehow measured imports, and then the percentage change. So when this thing is positive, high and positive, it means that this year, particularly, for example, here, sometime around 1985, United States started importing a lot more than previously. It was importing less and less than before, and then suddenly started importing more. Something changed. Unlike in 2010, when the imports declined, it was importing more and more over a long period of time. You see it by more and more and more. It was growing all the time. It was all the time positive percentage change over 1 year. It means that this year they imported more than last year. Then again, not as much more, but still more than last year, positive percentage change. More than last year, more. So there was a substantial trend, definitely a growing trend. And then suddenly, boom, in 2010, they imported about 15% less than last year. What happened? Well, there are some consequences of the crisis of 2008 and 9, changes in the. Can we say that this thing is stationary or not? Well, the original time series before the transformation to percentage change definitely was not stationary, because it's growing economy, right? We know, and the trade also grows along with the economy. Imports grow, exports grow, gross domestic products grow, national product, so it grows everything. So it relies on international trade a lot, that open economy. So of course it will be non-stationary, the import of goods overall. Moreover, it was measured, since it's not said anything about how it's measured, it probably was measured in just current prices, not in constant prices, right? So due to inflation, it will also grow or be non-stationary. But then we transform it to percentage change, short-term percentage change, like this year compared to the previous year. And this is a kind of change, a kind of transformation of a time series that often kills a lot of trending in the data. And we can see that now, yeah, there are no obvious signs of non-stationarity. There are some deviations like here in 1885, but then the series returns back to like its overall kind of stable level. There are also some deviations to the negative area around 2010, which is probably due to some crisis, but then again, it comes back. And over a long period of time, it stays like fluctuates around. Sometimes it's for substantial period of time higher than on average. Sometimes it's lower than on average. So maybe those are signs of non-stationarity, maybe not. Maybe those are just some deviations due to current events and other factors, but it doesn't mean that globally unstationary. And it is like 40 years of observations. So for a macroeconomic time series at such low frequency as annual, this is a very low frequency. Nowadays, it is very, very, very rare that than in the economic data we have to deal with lower frequency than annual. Mostly often annual frequency is the lowest frequency. Everything else is higher frequency. So sometimes there are biannual, but very frequent, very rare. Sometimes there are like semi-annual frequency, quarterly data, monthly data. bi-weekly, weekly, and so on. Depends on the statistics on the country, but for such a developed economy as the United States, yearly data for macroeconomic data, it's like the lowest frequency possible, and 40 observations, it's quite a lot. So there are not no obvious signs of non-stationarity. We might throw in some formal testing to confirm that it might be stationary, because we might not see something. It's not always easy to see how the time series evolves. And over a few dozens of observations, it's it might be very easy to confuse the unit root kind of non-stationarity with stationarity. So tests are required. So what do you think the tests say? Before going into the details of the tests, what are the conclusions about the rejection or not rejection? So there are two tests, two p-values. One is relatively small, one is relatively high, or both relatively high. What do you think? Okay, first about the second test, KPSS test. This is the easy one.
Stationary.
Why?
I think that we reject stationarity in this test.
As I said before, going into details of what is what, just rejecting null and not null, and then we will try to recall what are the nulls. So the p-value higher than any reasonable level of critical size, which is normally between 1 and 10%. This is a p-value too high, whatever the critical size is. When p-value is that high, we don't reject the null hypothesis. And the KPSS test now is stationarity, so we don't reject stationarity in this case. That's right. Don't reject stationarity, because the null was stationarity and we don't reject it. What about the first test? This is a more tricky thing. And unfortunately for us, with formal testing, there is like a convention. In essential judgment, we can like maybe be flexible a little bit and say, okay, this might be like that or like that. This might be true. This might be true. Sometimes the conclusion is obvious, sometimes not. But with the tests, yeah, so KPSS alone is not used. It's not considered a good practice to use KPSS test alone. So even if we see that there is something that already confirms our previous judgment, but there is another test that rejects it, it's like a sign that something is not going well. So what about the Adf test?
So p-value is below 0.1. So we can reject the null hypothesis about unit root, and it will be also telling us about stationarity.
We're more likely to say that that's not stationary.
Yeah, well, that depends on our on how strict we are to ourselves and to the test and so on. So this is an example of inconclusive p-value in some sense, right? So it is not too high for us to say that definitely we do not reject, like in the second case. It is not too low to say definitely reject, right? So it's in between those like endpoints on our critical size levels. It's between 1 and 2. It is even between 5 and 10. So usually if it's less than 5, okay, it is safe to reject. But in this case, like in common logic and the most common sense of the how usually the p-values are interpreted in practice, we should say that we should tend not to reject the null. And the null, in case of ADF test, is not stationarity, is the unit root, right? So ADF test suggests that we should not reject the unit root, which is not stationarity. But depending on how strict we are, because it's annual data, because it's macroeconomic indicator of a very low frequency, there might be some deviations. It might be very persistent, right? It might be influenced by other factors and so on. So the sample, even if the time period at hand is quite long, it's 40 years, almost 40 years. The sample size is pretty small and the test is asymptotic, remember. And unlike with the traditional z-test or t-test, when a few dozens of observations is already enough to say that, okay, the distribution is close enough to the normal distribution, or that CLT works and so on. So this size of distribution is critical here. The sample is not too high, too large. It is okay. It is what it is. With macroeconomic data, 40 annual points is like, wow, it's a lot.
So we have two tests which are telling us different
yes, exactly.
hypotheses.
So yeah, welcome to the real world. I'm like that Morpheus kind of guy now. That happens, and quite often. In this case, we have to gather everything that we know, and also remember why we arrived at this point, why we decided to run the tests in the first place. So first of all, we decided that this is already a transformation of definitely non-stationary thing that was trending, the original USA imports of goods statistics data time series, right? We transformed it to percentage changes to kill the trend. And now we are considering that detrended data or transformed data that is percentage annual change. There are some signs of deviations from something that looks like overall like a stable level over time, over a long period of time. But there might be some confusion with the non-stationary data, and we run the tests. One test says that, yeah, it is dangerously close, but not surely close to non-stationarity. But there's a tendency to reject, not to reject non-stationarity or to reject stationarity. And then we say we don't reject stationarity via the other tests. So there are more signs of stationarity, which is the essential judgment, the visual analysis, and one of two tests. But one of two tests says that, yeah, there might be some confusion with non-stationarity of this particular kind of the unit root. It means that we should take into consideration that, yeah, there might be problems with stationarity with this time series. It is okay to use it in the models as if it was stationary, but keep in mind that there are signs or like some behavior inside of it that this test, this particular kind of test for this particular kind of non-stationarity tends to put out as non-stationary. It is okay, it happens. So yeah, if I was about to use this data in a kind of model that requires stationary data, and this is like all short-rank macroeconomic models, either for prediction or for explanation or for like cross influences or something like that, I would use it as a stationary data, but keep in mind that it influences what? Stationarity is required for what we say it is required. It is required for all our results, all our tools to work. So when we evaluate the quality of our estimates of the models, when we use this kind of data, we have to keep in mind that, yeah, there might be some problems with some of the data that we use. So some judgments, particularly some estimates of standard errors, some estimates of the coefficients, some judgments based on limiting theorems they might not be as precise as if this was a definitely stationary time series. That's it. That's the most that we can do as economists and as econometricians. It is not as easy, like there is no easy conclusion, but this is how it works in the real life. So yeah. Yeah, so there were questions to go through. So what are the first steps that we saw previously and how do we interpret the results? I just said that, yeah, sometimes I forget about that there are slides in the presentation. Sorry. Another example with the same questions, and I think this would be the last example that we consider now about the formal testing. And I suppose later this week there will be some asynchronous material, because otherwise we are moving too slow. So again, this is an example from the previous lecture. The crude oil price. What was the, no, that's not the last example for today. It's too easy. What was the conclusion in the previous lecture about it? Do you remember?
It's not stationary.
Yeah, why?
Because it is influenced by new info. So heteroscedasticity is present, and also it is influenced by any shocks. So
heteroscedasticity, be careful with heteroscedasticity because it might be tricky, but keep in mind that heteroscedasticity is instability in variance. And variance is something that when you calculate variance, you remember that variance, what is variance essentially? Or like even technically by definition. Variance so of some value, it doesn't matter which one. By definition is the second central moment. Central means that it is taken around its mathematical expectation. And now imagine that we are talking about variance of a time series. So now that also has index t here everywhere. And to talk about stable or unstable variance, it first of all should exist. Or not just exist, or be meaningful, or be something that we can somehow observe. And if your time series is not stable in the mean, so this thing already changes each point of time, then it is perfectly impossible, like very close to impossible, to even observe the variance from the data, because at each point of time, something that goes inside the variance is unstable, it changes. And if it changes substantially, then you will not be able even to observe the level of the variance from the data. So the only thing when from time series we can observe level of the variance and say whether it's stable or not stable is only if this thing is stable. So always first think about the stability in the average or in the mean level, like something like this. So here, at least the average level could be somewhat long run stable around the same level. But then we can say, okay, the average level is stable, but there are periods of higher and lower volatility, of higher and lower variance. So even though it seems stationary in mean, it is not stationary in the variance. By the way, formal tests never test stability of variance. So whenever we are talking about formal testings, it doesn't consider stability of the variance. This is how the theory of time series developed. So now back to this example. So yeah, there might be some heteroscedasticity. Essentially, there might be heteroscedasticity. We know that, but from what we see, there's even huge instabilities on average in the mean level. Right? There are trends, there are shifts, There are changes of trends. There are some levels of stability that are changed very drastically, and so on. Arrival of new information, crises, and so on. And this is even essentially a very short answer. Of course, it's not stationary. It's a price level from a market. Price level measured at a daily frequency. Of course, it's not stationary over a long period of time, 15 years at least, even more, almost 20 years. Oh yeah. And it's very important for global economy markets such as oil market. Of course, yeah, it is influenced by so many factors, and there are going to be so many shifts in the dynamics. So not stationary. Okay, and then for some reason we decided to run the tests again. So this is something that should not even appear in your practical analysis. It could be like it could appear in practical report or practical analysis in the only scenario if you have like some set of time series data, different variables, different transformations, and you just have to report the full results of some tests. So you run tests for all the data that you have and you report all of them. Otherwise, it is not necessary. You should not even like arrive to the necessity to run the test because it's already obviously non-stationary. And what do we see from the results? You can memorize like this, like take a screenshot of this part of the presentation, this left panel of this slide. And this would be like your cheat sheet for non-stationarity for which test shows what. Because here the time series is obviously not stationary and both tests should confirm that. Otherwise, there's something wrong in our judgment or with tests. In this case, everything is correct. We know that this thing is not stationary. We can see that it is obviously not stationary from the data that we observe. Right? And the test confirmed that the ADF test rejects something.
It rejects non-stationarity. So it tells us
it rejects what?
Unit root.
Yes, so it rejects one particular kind of non-stationarity, which is unit root, in favor of something that is called stationarity. You remember that quote marks stationarity, like the not unit root kinds of stationarity, but this thing is affected by all kinds of non-stationarity that could be there. So again, so this is the like just the reminder of the thing that you should not arrive at the idea of running this test. Yeah, it might be a bad idea to use it as a cheat sheet because then you will confuse which test has which now. Yeah, okay, so let's not do that. But yeah, and KPSS, the opposite side, it rejects the what? It doesn't reject the null, which is stationarity, in favor of non-stationarity, and this is just some kind of what?
Our tests align.
Yeah, tests align, but they contradict the essential judgment. And again, they align around definitely incorrect conclusion. That's because you should not have run the tests for that conclusion. And if you do so, it is of course important to base your conclusion based on the to base your conclusion on the essential judgment first. Yeah, okay, so we don't have any more time. Unfortunately, there is another example. You can consider it later. This is from earlier today. You already saw that this is Gini index. I'll just comment it on myself. So this is a very rare case when ADF returns a very high p-value. And in this case, they again contradict. You see, both tests return high p-values, which means the results are going to be contradictory. And in this case, essential judgment should be more important again, as usually. But in this case, we were not able to make the final conclusion based on the essential judgment and the visual analysis. That's why we turn to the tests, and then we see this. So it's another complicated example, but somewhat like a little bit opposite to what we saw in the first one. Okay, so we will talk more about the examples and how to interpret those contradictory results and why it happened, why they happen, especially in the practice session over the two classes. Now, unfortunately, we don't have time. And in about some time, I have to switch to makeup exam of econometrics, and I see people already are coming like, why do you come like half an hour before the exam? Don't worry, we are not going to start without you. So if you have any questions now, please stay and ask. Otherwise, please follow the chat notifications in the chat. There will be some self-study material, and come to the practice session to discuss more examples about testing stationarity and more different forms of tests.
So the previous example is like how it is in English, like a trap of fool.
Yes.
Okay.
Exactly. This is the trap for people who tend to overtrust the statistical tests without knowing how exactly they work. And the idea behind the tests is that every test is based on some particular model which tests for some particular kind of non-stationarity or some particular kind of stationarity and might be oversensitive to other things. And when the time series is overloaded with, pardon my language, with all kinds of shit that can happen, this is what you will get. It doesn't mean that tests are bad. Tests are okay. You should arrive to the formal testing only when you passed through all the other stages. Yeah. So yeah, there is a short wrap up of this part of the lecture, and then there's continuation. I will fix the presentation and mathematical formulas and then upload a new version of it.
And may I ask you to upload them in PDF too, please?
Yes, but that requires fixing that mathematical stuff first, because, well, you know, otherwise PDFs are not going to be represented correctly as well.
Yes, of course. Thank you.
Yes. Okay, if there are no more questions, you are free to go, and I will prepare the exam because it's going to take place exactly in this room. So
Thank you. Goodbye.
Bye.
Goodbye.
И здравствуйте всем, кто уже на экзамене.